Hi guys, I just want to go and do some review here. This is part 2. Basically, this is lesson 25.2. And remember, we're talking about in 25.1 pair design. So we're doing difference of them. We're doing the mean of the differences instead of difference of the means in this unit. And so we're comparing when to use a 2 sample with a paired t-test. But I just want to remind you of a few things that will hopefully before we keep going, when to use stuff, what's happening. So just kind of maybe a breakdown of a couple of different things. So first of all, I just want to remind you of how we calculate standard error. So remember in chapter 23, we were doing about standard error for one mean. All right, so when we're doing that, that's just the standard deviation of our sample over the square root of our sample size. And then chapter 24, oops, didn't mean to go quite so low on that one. All right. Chapter, all right, we gotta sit there. I'm having issues here, people. This is when I'm glad I have my mouse next to me because it fixes everything. All right, sorry about that. Realize I just went up too high. So we'll just go right here, chapter 24. So we do the standard error, and this is when we do the difference of the means instead of the mean of the differences. All right, so we have, again, excuse me very much. So we have x bar 1 minus x bar 2 equals, and then remember we add the variances, so it's the standard deviation squared plus standard deviation squared, and then we take the square root of that. So it's sample 1 standard deviation squared over n1 plus standard deviation of 2 squared all over n2, and then we use that to find our standard error. But on 25, what's a little bit different for chapter 25 is we're doing the mean of the differences, and so it's the standard error of the differences, and so it's a little bit different. So remember, we take the differences of our matched pair, okay, so the two pieces of data that we're comparing, and we take the differences, and then we find the mean of all of those, and so it's our samples standard deviation. All right, so it's the standard deviation of the differences, so the data we get when we have the differences over our sample size, so square root of n. So hopefully that tells you a little bit how we progressed through how we calculate standard deviation. But we also have to do another quick review with this. Remember that d bar is the mean of the differences. So that's when we take pairs and we take the differences in our two pieces of data, and then we take the mean of all of those. So the difference, so mean of the differences. All right, now, when do we use matched pair design? Okay, so when we talk about being looking for the mean of the differences, you look in two spots. We look for blocking in pairs. When do we do that? We do that for experiments. And then we do matching in pairs for observations of things. So when we're doing an observational study. All right, and so that's when we call it a matched pair. That's when we get that. So hopefully that helped a little bit more when you'd see each one. So let's go back to this one right here, and let's talk about what's going to be the best type. Is it going to be with 2 samples or with doing a matched pair design? What's going to be the best one to work with? So let's read this one through together on number 17. Push-ups. Every year, the students at Gossett High School take a physical fitness test during their gym classes. One component of the test asks them to do as many push-ups as they can. Results for one class are shown below, separately for boys and girls. Assuming the students at Gossett are assigned to gym classes at random, create a 90% confidence interval for how many more push-ups boys can do than girls on average at the school. So a few things that we need to check out. First of all, we have to decide, is this probably going to be a 2 sample or paired? So here's my question. Are we pairing up with each other? No. So we have really basically 2 groups that we're looking at. We're looking at the guys and we're looking at the girls. So first of all, randomization condition. We assume that the students are assigned randomly at class. So they are assigned randomly. 10% condition, 12 boys and 12 girls, or less than 10% of all teenagers in gym class. The nearly normal condition is the histograms of the number of push-ups from each group are roughly, okay, now how do I know this? Well, this is when you're going to have to be really good at checking this. Unimodal and symmetric. So how do I do this if they give me a list like this? Well, remember, you put 1 in list 1, and you put the other ones, the girls, in list 2. And then you would go into your, oh, I don't have my calculator right here in front of me. Where is my calculator? Good question here. All right, grabbing it, even though that doesn't help you as much, but let me pull up tablet mode here for just a moment. All right, when we're looking at calculator, guys, see if I can get that to come above here. You have to be able to make the histogram. So where are you going to go? Well, you're going to go to second y equals. Remember our stat plot. And then you go to, like, for number 1. And so you'd hit enter. You make sure it's on. You'd pick your histogram. And then boys would be list 1. And the frequency would be 1 per list. And so you would do that. And then you would go zoom, right? So let's just say we're doing this. And this is not the right data. Because remember, I typed this in the other day in class. So we got all that in there. And then we go zoom, stat. And so you do number 9. And remember, you could do your histogram. Now, you would do that both for boys and girls. So you just do the list, you just change it to list 2 when you're doing it for girls. So let me give you kind of a rough idea of what that would look like. Let's say here we have for guys and girls. I think we're going to let 5 be the top number of our frequency here, and this would be like 2.50. So this would be the number of them. And so then we have our girls list here. The number of push-ups, I do believe, would be here. So this would be for the girls value, and the number of push-ups. All right, and so you'd have something like, I think between 20 and 40 are kind of where we're at, and you'd have something that looks, and I'm being very like wrong with this, but something that would look in a value of, I think we had 5, and then we'd have, what else do we use? Something like over here at 3, and you'd have another one down here. So we could say that one's roughly. And obviously, remember the bins, it should be labeled. You can get that from your histogram by using trace. And then we do the same idea, would have to be for guys. Because our sample's small enough, we actually have to show our histogram. So we'd have 5 again, and then this would be the number of push-ups. I think, is it push-ups? Yeah. And make sure, I was like second guessing, thinking it was pull-ups. And so again, you'd have something a little bit more, in this case, I think it looked more like this for the guys. But basically, are they unimodal and roughly symmetric? Yes. So the near normal condition has to be met for both of those. All right, the independent group assumption. The groups of the boys are going to be independent of the girls. We have no reason why to think they wouldn't be independent of one another. And the reason why we separate groups is we're not pairing them. It's not a competition between boys and girls. We're just doing overall comparisons. Since the conditions are satisfied, it's appropriate to model the sampling distribution of the difference in means with a student's T model. So we have our student's T model with how many degrees of freedom? Well, this is from technology, so we actually have to run the test and come back to it, but just to save us time, and if we do a test right, it's going to be 21.05 degrees of freedom. We'll construct a 2-sample T interval with, all right, and I think they asked us to do a 90% confidence on this one. All right, so let's do the work real quick behind this. So if you're doing this quickly, if you've already done what we're doing, you should have put the 2 list, okay? So you're going to make 2 list. And I'd put guys in list 1, or boys, you can say boys. That goes into list 1, and then girls go into list 2. Again, we should have already done that if we're doing the histogram. So you might want to pause this and just put your calculator stuff in. Then you're going to choose the 2-sample, and I can't remember what that value is for that, T interval, in order to do that. And then you're going to go to that spot, and then you're going to actually, you can use data for this. And choose data, and then list in. Boys, remember, going to be list 1, so that would be X1, X, 1, and so all would be a 1, and then X2 would be the girls, so X bar 2. So putting those in there, you let the list do the work for you. You could also do it this way. So we have our X boy showing our formula, X bar girls, plus or minus our degrees of freedom We'll put that in as 21.05 in a moment. And then our standard deviation, over square root of n, standard deviation of girls over the square root of n. And then we plug in our values for these that we get. So if you punch this into your calculator, double check. Now, I'm just saving time, I'm not putting it in the calculator right now. But I think we got, for the guys, I think it's like 23.833 is the mean. For girls, it ended up being like 16.5. We go plus or minus, the critical value for this would be at 21.05. Now, again, we'd have to use inverse what for this, guys? Inverse t. You'd end up putting our samples with this, and so it would take care of all that for you. So don't worry about that. So degrees of freedom are, they give us from our standard deviations, we get 7.209 squared over the 12 guys. Oops, I just wrote that down wrong. It should just be n here. And girls, sorry about that. Caught it while I was working on here. Hopefully you guys caught it earlier. Standard deviation 8.939 squared all over 12. Okay, so hopefully you'd work that out. Again, I would let the calculator do all the work for me on this one, but we can easily put in the information from our calculator to get this. And then you're going to get approximately, your interval is going to be between 1.6 296 and like 13.037. All right, now that's additional push-ups that guys could do over girls. So based on our samples, right? So based on the samples, we're 90% confident at Gossett High School the mean number of push-up that boys can do is between 1.6 and 13.0, more than the mean. And now this is where I did not do well. Insert right here. Number of push-ups for girls. Hopefully that makes sense. That was a confidence interval. That's not a paired one. Well, now let's look what one that's going to be paired. All right. So with this, let's see if I can help you guys get the next one down. So job satisfaction here. This one is actually using an example we used on the notes on Tuesday about this. And we said it doesn't work because we couldn't use the method that was in that chapter, but we can now because we have our paired design. So let's read this over again, and then we're actually going to do it quickly on the calculator. I'm hoping I can get it figured out without messing up too much on the calculator. It says, when you first read about this exercise break plan in chapter 24, you did not have inference method that would work. Try again now. A company institutes an exercise break for its workers to see if it will improve job satisfaction as measured by a questionnaire that assesses worker satisfaction. Scores for 10 randomly selected workers before and after implementation of the exercise program are shown in the table below. Identify the procedure would use to assess the effectiveness of the exercise program and check to see if the conditions allow for that procedure. Okay, first of all, since we're looking at the same worker before and after, that is a paired design. So we'd use a paired t-test. So when we look at that, that's going to be a one sample t-test for the mean of differences. This is what we're going to do. So the difference of the means, we're going to go the mean of differences. All right, so we have to check to see if this would work or not with this. All right, so first of all, randomization, the workers were picked randomly. 10% condition, assume the 10 workers are less than 10% of all workers at that company. We don't know that for sure, but if nothing else, they're probably, if they're randomly, they'd probably be, we're just assuming it's a bigger company, over 100 people work at it. The near normal conditions, if we could do, they actually did before and after. It's going after minus before, an improvement. The histogram, you could say, is unimodal and roughly symmetric, but it's nothing too exciting because there's not a lot of data there for it. But how in the world would I have gotten the fact that was unimodal and symmetric if I didn't do the work before? Well, guys, this is when you can use our information to help us out. This is when you get on your calculator and you'll put these in your list. You literally could go list 1 is before, and you do list 2 after, and then we'd make another column. So this would be your list 3, which is actually the differences. So like you could, now the difference is really, if you want to think about for your list 3, and you could actually plug this into your calculator. You literally could go on the top of list 3's column, you could go list 2 minus list 1, hit enter, and it would do all the calculations for you on this. Trying to save time here. I'm trying to figure out if it's best to show in the calculator or not, but let's just do, oh, no, yes. I'm trying to think, sorry guys, what would be the best one? Let's just put the columns here. So we got, actually, let's do it on the calculator real quick. Okay, I am changing my mind. I'm vacillating here back and forth, but oh well, let's do this real quick. Let's put the values in and make sure we have it. So let's go stat, edit, number 1 here. All right, I'm gonna go an arrow up here and I'm just gonna clear it real quick to make sure we're all good. All right, so now I'm gonna go put the values in here. So I got 34, enter, I'm gonna go 28, so this is the 4, so I'm gonna, oops, don't do that. Delete. It is actually a lot harder to use this in a regular calculator. All right, 28, enter, 29, and I'm just going to do both list here, and I'd advise you guys doing the same thing on your calculator. Make sure you're comfortable with it. 26, enter, what do we got here? 27. Going, we got 15. And I think I've missed someone. All right, anyway, so, all right, let me see, 34, 28, 29, 45, 26, 27, 24, 15. All right, we're at 15. And then we have 15. And then we're at our last one, 27. All right, so we do have everything that we need. All right, so I'm going to arrow over to the next list, and I'm going to put the afters on here. So 33, enter, 36, enter, we got 50, enter, 41, and we keep going through, 37, enter, 41, 39, 21, enter 20, and then we can have 37. All right, now here's the cool part about it. I can let the calculator still do all the work for me. So arrow up, and then we want to take the after and before. So remember, we want to go list 2 list 3 is list 2 minus list 1. I want to do the differences. This is the D. I haven't calculated the mean for it yet. All right, let me put this back up. So all you have to do is go, make sure I've got this one, go second, and go list 2, so number 2, minus second list 1. And that's being stored in list 3, so this you can see on the bottom of the calculator screen right there. Hit enter. It does all the differences for you. Now I can use that in order to calculate all my information that I need. Now let's do a quick stat plot on this one. Go second y equals, and let's see our histogram. So go to the first one. We're looking at list 3 though this time, so we just got to arrow down, change it to second list 3. I'm going to hit enter here. Go zoom. Remember to zoom 9. And that's basically what it looked like. Now, oops, I have a y equals on here. I need to take off here. Y equals. Where's my y equals? I need to clear these things. All right, I'm going to go zoom 9 here again. A little bit easier so I don't have to look at it. All right, so that's it. Now, it doesn't look as nice as what it did before, but we do have negative values on this. So one thing you can do one time and it'll look very much, just zoom out once. And you can see a little bit more the differences on here. They used a lot bigger bins than what we did, but remember, you can trace it over and you can easily see like where's your trace, and you can totally do those values. So you can just trace it and it will get you what you need. So very easy for us to do. So again, don't overly worry about that. It's close enough, unimodal, roughly symmetric, great. But that's how you can do it on your calculator. Now, let's test the hypothesis and conclusion, which we're going to go back on the calculator in just a moment, okay? First of all, what is going to be our hypothesis here? We know the mean difference we think is not going to change. So we say the mean difference in before and after job satisfaction scores is 0. And the exercise program is not effective. Oh, actually, I'm not writing this so it makes sense here. Sorry, is not effective at improving job satisfaction. So we're sitting there saying with this one, delta naught, you can say delta naught if you wanted to. Delta naught is 0. Or if you want to say our mean of the differences is going to be at 0. Okay. Also, though, when we're working with it, we're saying, though, the alternative is for the mean differences, and this is really what the company is looking for. And before and after job satisfaction score is greater than 0, and the exercise program is effective at improving job satisfaction. So we're in the mean be greater than 0. All right, so we've met the conditions up above. So we said since the conditions are satisfied, the sampling distribution of the difference can be modeled with the student's t-model with 10 minus 1 degrees of freedom. So the reason why it's 9 is how many people did we randomly look at? 10. Okay, so it's degrees of freedom. So this would be our model, and this is one way you can write the model out and it works. So we know this is going to be at 9. Our mean is going to be at 0 because there is no difference. And what is going to be our standard deviation? Well, that's where you can get it from your calculator again. So this is where it's really kind of cool. Let's let the calculator do the work for us. All right, guys, go stat and go to test. Okay. All right, now what type of test are we going to use? Well, we're going to use a t-test, but we're going to throw the values in for mean. So this is the cool part about it. So go to your t-test. So go to number 2. We're going to input with our data. Our mean not is we're going to assume that it is 0. We're going to get our list, though. This time is from list 3, because remember, that's where we took the differences from. So second, list 3. Frequency, and we want to show, which way are we looking at again? I think it's supposed to be greater than. So let me arrow it down here. Hit enter. We're going to calculate. So notice all the information that we got from this. We got our t-score of 3.597. So that, guys, that's way to the right. Remember, that's like your standard deviations away from the mean. All right, so we have that value. Then look at my p-value. It's 0.002. My mean is 8.5. My standard deviation for it is 7.4217 out of a sample 10. So all of this stuff is going to go into my formula that we need to show. So wish I could screenshot that right now, but it's not going to be very helpful. But that's where we're going to use the values. So the test did everything for us, and the p-value is low, so we're going to end up rejecting it. But we got to show our work now. So we're going to use a paired t-test with this, or you can say one sample t-test for the mean of differences. All right, is the other way you could say that. All right, so we know d bar, our mean of the difference is 8.5, so we put it in here. We got 8.5. We said our delta naught was 0 when we're working with it. Our mean, which we found on our calculator, actually, let's do it this way. Let's just do what our formula is first. Remember, it's d bar minus 0 over s of the mean. Still, let's just go standard error of the mean, so it'll be so much easier, of the mean of the differences. So that's going to be 8.5 minus 0 over, well, what did we get our value to be? It's 7.47217 all over 10. And that approximately gave us like 3.6. It was 3.59, whatever. So 3.60, I think we're going to say close enough. Now, what would that look like? Well, first of all, it's a t-model. So we're going to say this is t-model at 9. We're over here. Here's at 0. We know our value is over here at 8.5. Our t-score, which is right below that, is 3.60. Our p-value, when we punched it into the calculator, was something like 0.0029. Guys, would you reject? Yeah, look at the value is. It goes since, and this is our conclusion, since the p-value of 0.0029 is low, or you can say is below the alpha level of 0.01, even if you wanted to, or 0.05, we reject the null hypothesis. There is evidence that the mean job satisfaction rating has increased since the implementation of the exercise program. So that's, remember, we talk about our evidence based off of our alternative hypothesis content. Now, and your conclusion turns, if your conclusion turns out to be incorrect, what kind of error did you make? Well, we made a type 1 error, right? Because if we rejected the null hypothesis and we're not supposed to, that's a type 1. Remember, type 1 error is failing to, incorrectly rejecting the null hypothesis. So that would be type 1. So we conclude there was an increased job satisfaction rating. If we were wrong, that actually there was no increase, we have committed a type 1 error where we rejected when we should not have. All right, guys, so make sure you know, again, the difference between type 1 and type 2 errors. You notice they still keep coming up. Remember, type 1 error is incorrectly rejecting the null hypothesis, and type 2 is incorrectly failing to reject the null hypothesis. Guys, I hope studying goes well, and that I will see you after spring break. Don't forget all the things you have to get done. You need to start studying. You can, if you want to, start studying for the unit test when we get back, but we'll do a review day, and we'll finish up those things, so don't worry about that. Make sure you're working on that multiple choice exam portion, practice exam. You need to do all the problems, then you grade it. The answer key is online, and then you go and you correct it with your resources that you have. I don't expect perfection on this because we haven't covered everything yet. We still have a couple more chapters we have to cover on the material. Hopefully, guys, we are all on the same page now with this. Also, chapter 25 homework, I'm not going to make it due until the Tuesday we return. So if you're gone out of town or something like that, you don't have to take your book with you or whatever you need to do. So hopefully that helps. You guys have a great spring break. Just be praying for me as I'm on my missions trip.